We have one more topic to cover with dot products, and that is projections. So we've got two vectors, A and B, and I'm going to represent them as both having the same initial point. And the question we're asking here is how much of B is in the direction of A? And that is exactly what we mean by the projection. We see how much of B, if B goes from here to here, how much of that distance, how much of that motion is happening along A. So the vector of projection of B on A, denoted by PROJ, sub A of B, that stands for projection, is the portion of B parallel to A. So if B goes in the same direction of A, or at least along the same direction of A, the projection of B goes in the same direction as A. If B goes sort of away from A, then the projection of B along A goes in the opposite direction to A. But in either case, it's parallel. And how exactly do we find this vector? Well, we can imagine there's sort of a light source that is shining down perpendicular to A, and we looked at the shadow that B casts due to the light source, and that is the projection. We take a perpendicular and we drop it down to the line that goes through the vector A in both of these cases, and then the projection of B along A will be the vector between the initial point and where this perpendicular hits the line that goes through A. So that's our projection. Now the scalar projection of B along A is the quote-unquote directed magnitude of this vector. And by directed, I mean we take it to be positive if we're going in the direction of A, and negative if it's going the opposite direction of A. Well, looking at this picture, it's not too difficult to see that this scalar projection, which we denote COMP, that stands for component, so COMP subscript A of B, it's equal to the magnitude of B times cosine of theta. That's because we have a right triangle here with hypotenuse equal to the magnitude of B, and this angle here is theta, so this side is the adjacent. It has magnitude cosine theta times this magnitude. Great. In this case, cosine of theta is going to be negative, but it will have the same magnitude as this supplementary angle here, so that's why this formula still works out in the case of the projection going the opposite direction. It will be a negative number. But if you do some algebra, you can see you can multiply top and bottom of this expression by the magnitude of A. And the top here, magnitude A and magnitude B times cosine theta, simplifies to A dot B. So A dot B divided by the magnitude of A is equal to the component of B along A. And therefore, the projection of B along A is that directed magnitude times the unit vector in the direction of A. We take the unit vector in the direction of A because then when we multiply it by this directed magnitude, we get the correct magnitude of the projection. And you can sort of multiply things out, and at the end of the day, what you get is A dot B divided by the magnitude of A squared times the vector A. That is what the projection of B along A is. Let's do an example. Let's find the component of B along A and the projection of B along A, where A is the vector with components 1, 2, and negative 2, and B is the vector with components 3, 0, and 1. So for both of these things, we're going to need to compute two things, A dot B and the magnitude of A. A dot B is 1 times 2 plus 2 times 0 plus negative 1 times 1, which is 3 plus 0 minus 2, which is 1. And, excuse me, the magnitude of A is the square root of the sum of the squares of the components of A. So that's 1 squared plus 2 squared plus negative 2 squared, which gives me 1 plus 4 plus 4. That's 9, and taking its square root, I get 3. So the component of B along A is A dot B over the magnitude of A, which is 1/3. So that means that the magnitude of the portion of B that goes in the direction of A is 1/3. And that's quite a bit smaller. That's 1/9 of all of A. Then the projection of B along A is A dot B divided by the magnitude of A squared times the vector A. So a dot b is 1, the magnitude squared is 9, and a is 1 to negative 2, so I have 1/9 times 1 to negative 2, and we get 1/9, 2/9, negative 2/9 as the components of the vector, which is the projection of b along a. So here's question 1. I would like you to find the component of a along b and the projection of a along b. I would like to note something which is pretty important about the projection, which is while the projection of b along a is parallel to a, if we subtract this portion of b parallel to a from b, we're left with a vector that is perpendicular to a. So b minus the projection of b along a is perpendicular to a. To see that this is true, I run through an argument. The idea is that a dot the projection of b along a is equal to a dot b. So when I take a dot this entire vector, I get a dot b minus a dot b, which is 0. So I'll just run through the argument. A dot the projection of b along a is a dot the vector a dot b over magnitude of a squared times a. And when the dot product, I'm allowed to take constants, scalars, and a dot b over the magnitude of a squared is a scalar. I'm allowed to take those outside and do the dot product. So the two vectors I'm actually dotting in here are a and a. It just so happens that there's a scalar multiple of a right there. So I pull that out, and I'm left with a dot a over the magnitude of a squared times a dot a. Well, a dot a is equal to the magnitude of a squared. The magnitude of a squared in the bottom cancels out the one with the one on the top. So this is just equal to a dot b. So the dot product of a and b is the same as the dot product of a and the projection of b along a. So when I take the dot of a with b minus the projection of b along a, I end up with a dot b minus a dot b, which is 0. So here's our picture. The projection is the part of b that goes parallel to a, and b minus the projection is this perpendicular piece right here. So the projection really allows us to decompose a vector b into the part of it that goes in the same direction, or possibly the opposite direction as a, and the part of the vector b that is completely perpendicular to the vector a. Let's do a physics type example, and I haven't done serious physics for a long time, so this may not be the best or most efficient or normal way of doing this sort of thing, but whatever, this is the way I'm doing it, and it works. So let's take an inclined plane that makes an angle of pi over 6 with the ground, and we'll put a 10 kilogram weight on it, and let's find the portion of the force due to gravity that's perpendicular to the plane. So I can decompose the force due to gravity, which is just pulling straight down to the ground, and I can decompose it into a part that's going along the plane, sort of pulling the weight down the plane, and then a portion that is perpendicular to the plane, and that portion of the force will be canceled out by the normal force of the plane pushing back up against the weight. Alright, so to do some vector analysis here, I need to represent the direction of the plane by a vector. Let's take a unit vector. Since we're dealing with just motion in 2 dimensions, I'm going to let y represent the vertical axis so that I will represent a unit vector in the horizontal positive direction, j a unit vector in the vertical direction, up. So then a unit vector in the direction of the plane going this way is cosine of pi over 6 and sine of pi over 6. That, you could get that by assuming that the hypotenuse of this triangle is 1. So then this side is cosine of pi over 6, this side is sine of pi over 6. Sine and cosine. So we get cosine of pi over 6i plus sine of pi over 6j, and that's root 3 over 2i plus 1/2 j. Now the component of the force of gravity vector that is along the direction of the plane, that is along u, We can get that by taking the magnitude of this vector times the cosine of the angle between the force of gravity vector and the plane. Since we're taking the direction of the plane to be this way, we'll get 2 pi over 3 is the angle between them. So cosine of 2 pi over 3 is negative 1/2. The magnitude of the vector negative 100j, well, j is a unit vector, multiplying it by a scalar of the scalar negative 100 increases its magnitude by a scale of 100. So its magnitude is 100. 100 times negative 1/2 is negative 50. So the projection of the gravity vector along the plane oriented this direction is going to be negative 50 times this unit vector u, which gives us negative 25 root 3I minus 25j. Then the portion of the force due to gravity vector that is perpendicular to the plane and therefore perpendicular to u is going to be negative 100j minus this vector, the projection of negative 100j along u. So subtracting that gives us negative 100j minus negative 25 root 3I minus 25j gives us 25 root 3I minus 75j. And so that represents sort of this vector right here.